We were looking for oscillators, and important oscillator which is used in most of the circuits, analog system as well as digital, is a VCO shown here, which is a tuning LC oscillator. And here the capacitor is essentially created out of a diode which is called varactor, because it's a variable capacitor with voltage, okay, or variable reactance, okay, or varicap, the other word. Now if you know a PN junction, depending on whether it is a abrupt junction or it is linearly graded or exponential, the reverse bias capacitance can be given by zero bias capacitance divided by 1 upon 1 plus VR by phi B, where phi B is the built-in voltage of the junction, VR is the reverse bias, and M is the factor which is decided by the kind of junction I have. For example, abrupt junction is half, linear graded is 1/3, and in between it may vary from 0.35 to 0.5 depending on the grade you get constant you get there. Typically in most cases 0.35 or 1/3 is shown, because the exponential function in a long range acts like more like a linearly grades. But it's not 100% true, because if it is a error function profile, it may be slightly different. Gaussian may even little different than exponential. So please take it that values are normally provided by the technology people for their device. If it is half, then it is much easier to find. 1 upon c square v is a straight line, so the slope is the m factor there. Okay, so now with this, in this case the diode, the VR essentially stand for the reverse bias. Phi B is the built-in potential which is for the given junction of source drain in the substrate. That's the same diode I'll use. That may have the typically 0.7 volt or 0.65 volt kind of built-in voltage. And so I just have to vary the control voltage to get variation in capacitance. And remember, larger the voltage I apply, smaller is the capacitance. So the range up to which I can do is from the CJ0 to a lower capacitance, that is higher frequencies. So at CJ0 it has the lowest frequency, and as I increase voltage, the frequency will also increase, because capacitance will decrease 1 upon 2 pi root LC. So C decreases, frequency increases. Of course, for a too large a voltage, breakdown may occur, and normal PN junctions in a CMOS technology may have a breakdown of 6 to 10 volts. So don't go beyond 5 volt or something. Okay, normal devices do not permit more than 5 volts. I can make diodes which are as they are called power rectifiers, can stand 5000 volts, but this is not a power rectifier. Okay, so it's a diode which is out of, and normally even each PN junction is surrounded by an N plus region which is called guard ring, which does not allow currents to spread out the reverse current. Okay, so some other technology someday, but this is what essentially, and so it limits the breakdown for very low values. So typical voltage which you can apply is 5-6 volts and no more. So the variation with this, whatever is possible, that's the maximum range, tuning range, which this CMOS technology will allow you for the VCO. The little bit of maths be of interest, which we already done, but I repeat it again for the clarity. This is called mathematical model of a VCO. We know if I write a voltage V is equal to Vm sin omega t or cos omega t has a unit of phase, that's what it is, omega t. So one can say that d phi by dt is essentially omega. Rate change of phase is essentially the frequency or angular frequency. So if I plot phi versus t, and if it is this kind of relation exists, it will be a straight line. That means the frequency is constant, and corresponding to this you may have a sinusoid which may have a peak voltage of Vm here. This is Vm sin omega t or cos omega t, depends on whether it starts at 0 or it starts at halfway. Okay. Okay, so this has a frequency decided by, you can see the way it is. The phi actually represents the frequency. Is that the phi t curve essentially represents the frequency. Pi, 2 pi, 3 pi, 4 pi, correspondingly d phi by dt is constant here. So his sinusoid actually has the same frequency. So you can see d phi by dt here, one angle, 2 pi, there will be one sinusoid and it repeats. Now if I have two signals, V1 and V2, which have different frequencies, omega 1 and omega 2, or has two phases, phi 1 and phi 2. If you look at this is just to prove what I made statement. This has a higher d phi by dt, or this has a higher, phi 2 has a higher d phi by dt than phi 1, slope is higher there. So if you can, I can do the same thing here for pi, 2 pi, 3 pi, for each such angle I figure out the frequency, and you can see from here for d phi by dt higher, this point is on the left compared to the lower one, which means the frequency of d phi 2 by dt will be larger. You can see from here this has a larger frequency compared to this one. So essentially slope of phi decides the frequency of operations. This fact we actually utilize in PLLs. Okay, that's what we do. Phase and frequency are related. So if I can control phase, then I can control frequency. That's exactly what we are looking at. So this figure, is this point clear to you? What I said, that if I have d phi by dt larger or smaller, it essentially means the frequency is larger or smaller corresponding to it, and that can be depicted. If you have drawn this, of course this is very trivial, this you can always draw two lines, put 5 pi 2 pi points, and you can see the frequency here is lower compared to this, which is because larger d phi by dt will have higher frequencies. Okay. This is just to prove that point which I said and given in many books including Razavi, Boyce, Baker and everyone. So the statement I am making, d phi by dt omega, is a valid statement. Okay. And therefore we can represent any phi t curve, okay, this is t curve, into its equivalent omega curve. Okay. So we say if this is a slope, then it has a frequency omega 2, higher slope, it has a frequency higher than omega 2, which is omega 1. As long as this slope is maintained, frequency is omega 2. Let us say same phase, same slope again occurs, so you go down to omega 2, again it rises with the same slope, then if it is different, it will have a different frequency. So this and this are essentially same. Okay. So mathematically if I say d phi by dt is omega, so integral of phi is equal to integral omega dt plus integration constant, which is phi 0, which is called initial phase at t is equal to 0. In a VCO, we have done this expression earlier, that omega out is omega 0 plus some constant of the VCO, KVCO, into V control. This is the principle of VCO. Now we have a oscillator output which is, say, let us say given by Vm cos phi t. So I represent cos phi from here in this expression. Okay, so I get Vm, capital Vm maybe you can take because I use small m again. So if I write Vm cos integral omega out dt plus phi 0, so I now say the output voltage of an oscillator has this kind of representation. Is that clear? If this is what you agree, then this is what you should also agree. Okay. Why are we trying to do? We want to figure out, and this is very important, and that's why PLLs are used in fact. Our worries are, if let us say this control voltage which I am going to apply is not constant. Right now, for example, if I substitute this, okay, I think I made cos omega, okay, I will have to write now cos omega, this omega out in here also. So maybe I do that first. So if I write this V capital M cos omega 0 k VCO integral V control dt plus phi 0, this is the expression I will get for V out t. If V control is constant, then there is not much an issue, okay. But if it's not constant and noise overrides, okay. So let us say generally the way it is expressed, assuming right now phi 0 is 0, initial phase is 0, V control has Vm cos omega t as its voltage, which is a sinusoid controller, okay, which may be overriding the DC value of V control. Now if that happens, I substitute for V control Vm cos omega mt here in integral, expand it, integrate and expand it, and leave some terms which are smaller. So I get it is V capital M cos omega 0 t, V0 sin omega t, k Vc0 Vm. You can expand and get this kind of expression. Just put this integral here, expand small term be neglected, and you get this. Now if you see now, I can further do little adjustment here, and this can be then written as Vm cos omega t minus k Vco Vm upon 2 omega m into this cos omega, this is omega 0 plus omega m term and omega 0 minus omega m term, okay. If omega m is not present, this whole term will go away and what you were expecting would be essentially received. So control is constant, you have a excellent oscillating frequency at omega 0. But if V control varies, you have two other frequencies surrounding it which are called sidebands. These are essentially noise bands, okay. So some energy will be lost in sidebands, okay. So in many cases, how do I retain control voltage constant or noise free? That is essentially what we are saying we will do it through PLL. Is that clear? So this whole issue of maths was shown to you that if there is a change in control voltage, that reflects in sideband power which is lost to you, because remember if this is not present, all the power would have in the spectrum would go to omega 0. If not, part of the power will go on the sidebands. Now this is worrisome in real life, and one must actually see that your frequency does not change, okay. Of course there is a word which, of course when it comes I will talk to you a little later, okay. So is that clear why I am trying to see that why it should be some locking has to be done for the reference which I am creating, and that is done through a system which is called phase locked loops, okay. Of course they have many other features, we will see a few of them. As far as this course is concerned, this is good enough. PLL may not be, of course except for the bonus part or some small queries, no mathematical theory, because it's a huge area. I can actually spend at least 6 hours to 8 or 9 hours only on PLL designs. By the way, most of the Indian so-called startup or industries in Bangalore, Hyderabad, Noida essentially are making PLLs of different varieties, different IPs they create. That's their major bread and butter. So don't think PLL is very trivial, okay. PLL is very strong chip which so many people need at different applications. So is that point clear that there is a sideband power loss if control voltage is not retained constant. So I start with phase lock loops, as I say. For most of you people may not be aware, but this was invented as early as 1930. So it is not a very new thing or something. Phase lock loop word was known, and even circuits were made as early as 1930. However, the first IC PLL came in 65, and first digital PLL in which digital signal were locked appeared in 1970. By the same year 1970, even sinusoidal or analog PLL were observed or actually made, and similar time there was another PLL was used in optical signals, and they were called optical PLLs. So it is not just electrical signal. Phase lock loop does not have to do about electrical signal. Any signal you somehow phase it back, adjust it, you get it called PLL, locking. Okay. So these are something where you can use it to lock the VCO frequency. I want VCO to be constant, or whatever frequency I am using, that should be constant. VCO may generate something, but I want that frequency should be constant of my choice. I decide what is my frequency. Using VCO and PLL, I can actually synthesize. I can increase the frequency or divide the frequencies. Okay, so it's called frequency synthesizers. And almost every mobile phone or every television or every other kinds of receiver, pagers, telephony, optical transmissions, everyone uses PLLs in one way or the other. And as I keep saying, a small company called Core actually have 80 IPs produced last year on PLL. Just take a small company of 24 people, of which 4 are IIT students, and they produced 80 PLL chips, okay, as an IPs. So you can see the business itself only for that company, small company, is on PLLs. Okay, so don't think this is trivial. This is very money making system right now. A typical definition of a PLL, since I am not teaching this as a part, so I did not prepare heavily for every word of it. So some game hai, theek hai. As I say, if you really need some, maybe next semester mixed signal course, you insist that they should teach you there. If he or she who doesn't want to teach that, I will come and teach that part. Okay. This is very important area for me. I like this. Many of my students have developed his PLLs, so I will like to actually tell you what's the problem. PLL is essentially a feedback system. That's what I say control. That means it must have some feedback control. It compares the output phase with the input phase. Please remember, phase and frequencies are related. Is that clear? So don't think that phase connection is this. The comparison is performed by what we call as phase comparators. Okay. FC, we'll say phase detector first, and that will compare as well. So we call PD or FD. FD is called frequency detectors. P stands for phase detector, and together we call PFD, phase frequency detectors. Okay. Normally phase detectors are sufficient, but much more accuracy and much longer range capturing if you want, you may need a PFD. That also can be a fully digital circuit, which is called charge pump method some other day. Okay, so phase comparator is essentially what we are looking for. I suppose some of you are communication, so you must be aware of these two terms. But for microelectronics student, it should not be Greek and Latin. So let's see what is a jitter and what is a phase noise. This is something which I always want to tell people. There is a confusion and there is not a clear understanding between the two, though they are similar if not same. So please, our major worry in all analog designs are occurrence of jitter, or equivalently saying occurrence of phase noise. It's very difficult to handle these jitters or phase noise at very high frequencies, and we are working these days on gigahertz. Is that correct? We are working on gigahertz, and at those frequencies this is very difficult to handle. At lower frequencies, this typically I may tell you there is a word which is common. Anything below 1 megahertz, the change in frequency or change in phase is called drift. Okay. And if you are my timer, we used to call wander. It's wandering. Okay. So now it has changed to drift. Okay. But anything beyond 1 megahertz, it is actually called jitter or phase noise, depending on which way we explain it. Please remember, even on the board, if you have a chips and interconnects, PCB for example, these two parameters, they are, as I say, essentially similar but not same. They are very important in board designs. So now remember, the board design of 90s or 95s have become chip designs of 2000 plus. Okay. Because now you have integrated more, but the same issues which were occurring on the board has now come on silicon itself. So the design issues are same as we earlier looked into board designs. Okay. So let me tell you what exactly is these two words which comes into our mind, jitter and phase noise. I will not derive the expression for this. How to derive one from the other, look from some Google paper, you will get it. Let us say we have a pulse of 100 megahertz, and let us say duty cycle of 50%, that is square wave. So we believe that if it is 100 megahertz pulse, the pulse period should be 10 picoseconds. We believe that actually, and it alternates at every 5 picoseconds. H should come in every 5 picoseconds. But this is only if you think you are right, that is ideally it should happen that. And if it does not, the difference which is going to come is essentially called jitter. So here is one I have shown you. This is your ideal pulse which you are expecting. This is the period. Okay. Now what happens in actual transitions, there can be an early transition or there can be a late transition. Okay. So the maximum early to late transition width in time is called jitter. There is an early transition, there is a late transition. The maximum difference of early to late transition is called jitter. Okay. Ideally what should be jitter? 0, because I do not want all transition to occur at 50% duty cycle if I fixed it, okay, at T by 2. But if it does not, what is the range in which this can change and any time change essentially we will say T plus delta T or T minus delta T, which is equivalently saying in omega terms there will be a change in phase for that. Okay. Omega T plus something means time shifts means phase shifts have occurred. So jitter essentially gives you phase shifts. Okay. Those who are communication again, they know much more about this, but from microelectronics side, few more words are important for both jitter and this phase noise. If you are written down, as I said, these are interesting part, and I do not want to spend hell of a time on these, but I wish I would have time enough to really teach you a PLL. Something, in digital I like to teach memories for long. Same way here I want to teach PLL, but somehow my course was so organized by me, I had no time left to PLLs. And I was told by mixed signal people they do teach that, so hopefully they will. In case you take, that is also an elective. So in case you need, you can. Okay. All RF people, all analog people, all digital people need a PLL, come what may, okay, irrespective. If it is only digital, we say DLLs. Okay. But DLL has also one other name called delay loop locks. So there is a difference there also. So please do not confuse with DPLL and DLLs. Some books do not differentiate. Okay. Okay, is that okay? This is trivial. So jitter is the maximum spread of time in which signal can shift from high to low or low to high is what we call as jitter. There are two kinds of jitter seen. One of course is deterministic. The other is always the random one. Okay. Typical deterministic jitters are crosstalk, two lines close by, signal going across, one can have mutual coupling between the two, and depending on the direction of signal going, it may have larger coupling or a smaller. If they are opposite in direction, they will have larger coupling. They are in same sense lower coupling. Forward crosstalk, reverse crosstalk. Forward is easy comparative to maintain. Reverse crosstalks actually boost the values too much and difficult to organize them. Of course, then there are EMI, electromagnetic radiations, interference as the word goes. These EMI radiations may come from the next line which is resonating at high frequencies, or may come from other systems around in the block. Okay. Other chips can actually have this, or in a dabba of microprocessor or such thing, other including power supply may actually emit EMIs, EMs. So if there is an EMI in signal path, we actually get into jitters. And same way word is, if not electromagnetic, even the noise, simple noise can be coupled between the two because of mutual couplings. So there will be noise surrounding which may actually overread the EMI radiations coming from outside. So they are similar but different sources. And finally, there are two digital people are most worried that in a block of circuit, you have lot many inverters or lot many this, all of them switch one go, okay. Out of 8, let us say you have quad or 8 in 1 and 8 switch together. They may lead to two major worries there we call power supply droop and ground bounce. That is the Lero will shift up, power supply voltage may go down. Okay. These are also essentially deterministic. They may lead, any change in anything will lead to jitters. Okay. The other of course is random, and in general if you are from microelectronics we always look into the upper part which we think we probably have some control. If you are a communication plan, he is very happy here or she is very happy here, no control. So she is very happy, he or she is very happy. Random is essentially maybe because of the temperature, maybe because of process variation, maybe because of the interface states, different interface states, okay. And since it's random, most likely it follows Gaussian in nature, Gaussian distribution it picks up. And since there can be more than one jitter sources, so average value if you have to calculate is called RMS jitter. Okay. Please remember these are like a noise, so noise is added up, so same way this is also added up. So jitter is something, this of course deterministic jitters can be drift, whatever it comes we can offset it, we can some compensations, we know how much so we compensate partly. For example, if you want crosstalk between any two interconnect line, put a ground line, okay, space, extra space, but every signal line is surrounded by shield which is the ground line. In normal cable you have shield, on a chip there is no shield, so you actually every alternate line is a ground line, okay. So only link between ground, no signal on that, okay. So that is how coupling can be minimized anyway at the cost of board size or silicon size. The second part is phase noise, which is as I say is a related term but not same. So if you have a variation in signal timings, they can also be represented in frequency domains, and normally they show a Gaussian distribution of this kind. This is let us say I have an oscillator whose power is shown here against frequency. If there are no jitters or there is no noise, all the power should have gone to the tailored frequency which is my center frequency f0, okay. So at that time oscillator will oscillate at that frequency, so no issues, fine, everything. But if there is a distribution like this as shown here, some power is actually given to adjacent frequencies which results in sideband. Just now I showed you this same word shown here. So now we define a phase noise out of this. You can see what I do is at this frequency of whatever band it has come f0 plus f1 fm, here I take a bandwidth of 1 hertz and figure out what is the power density there, total power, and then integrate all the power which would have actually have got integration of total this power, and ratio of the two is called phase noise. Is that figure drawn? As I said, this is not necessarily part of our course per se in design, but good designers must be aware of everything this, otherwise when things do not work we do not know on what to explain, okay. It may still not work, but at least we should be happy it is not working because of this, okay. So that because word is how we know about, okay. And this spec is specifically normally given to VCOs, how much phase noise available allowed, okay. So it is not that this is not a spec, this is a spec, okay. So phase noise is defined as power in 1 hertz bandwidth of offset frequency, that f0 plus fm is the offset, okay. At that 1 hertz bandwidth, okay. If you find the power there divided with total power of the carrier, okay, then it is called the phase noise, and it is always expressed as dB with reference to carrier divided by hertz, okay, dBc per hertz. So we must actually design like an error. If you are solving a numerical analysis, what is the way we do it? Within this truncation error or what is the error bar, we say okay truncate things. So ये PLL भी एक पर्टिकुलर एरर में स्टॉप हो जाता है, उसको बोलते हैं कि व्हाट इज द परमिसिबल फेज एरर, 5%, 1%, 0.5%, you decide, okay, that much time it will go through loop and will actually settle. ये actually 0.5% है, sorry हाँ, most permissible phase error is 0.5%. Okay. Now there is a circuit which is shown below which is more like a PLL. We have a summer here, we have a low pass filter, and we want to have output frequency same as center frequency. VCO's output frequency should be the same as, and there is a variation in input frequency from the center frequency. So as soon as that small delta t occurs, this loop will operate and will bring center frequency to close to VCO frequency, okay, or rather opposite. The VCO output will be exactly same as your reference output or frequency you want. Even in jitter, there are few other words which are of interest to some. This sigma part is essentially what it does by a detector, phase detectors. No, this delta t is in the omega form itself, 0.5%. That is at the phase for the center frequency, whatever is the phase acceptable to you is 0.5%. That is, let's say I have 1 megahertz, 0.5% equivalent phase, whatever is allowed. Their lock should stop. Let us say 1 megahertz, 0.5% change is 0.99 megahertz, 0.996 megahertz. We don't want to go beyond further to make it 1 megahertz. So lock should stop there. Ideally it should be 0, it should lock exactly at that frequency. But it may not, because the components can never give 100% locks. So थोड़ा drift रहता ही है, but that should be permissible for you. Okay. Jitter वाले भी थोड़े लोग अलग अलग statement देते हैं, थोड़ा ये भी है. There is a word which they say cycle to cycle jitter. Like for example, here it is d plus delta t1, the next time it is t plus delta t2. Okay. First of course is RMS value, so average value of that is average RMS, not average, RMS value is normally taken for peak to peak, or RMS, two values of jitters are measured. Then there is called accumulated jitter. Over a given time, after certain cycle, how much is the net jitter occur to you? It's called accumulated jitter. For example, here you can see now it is small at the end. This may be large enough a jitter, and that may change your final phase itself. Okay, so that is the accumulated jitter is also specified, 5%. Okay. Of course, then there is a jitter in duty cycle distortions. 50% may become 49, 51. That also can create more problems. Okay. So these are essentially, as I said, terminologies in PLL books or PLL chapters if you read in an analog book. As I said, we are not going into huge detail of that, some other day, some other time, for some other people. Okay, so here is a phase detector part which essentially is shown here. You have two signals V1, V2 which passes through a phase detector and create an output. And the way we actually are looking right now is the phase difference, which is delta phi, and the average value of this V out should be linear. Now definition, because this is one which is going to control the VCO frequency. This is the control signal of VCO. Okay. Typical phase detector could be as simple as an XOR gate. If you have two signals V1, V2 in this square form, you can see at this is an XOR. So whenever they are not same values, the output go 1, otherwise they are zeros. Since there is a jitter between these two, at this frequency this is 0 but this is 1, so it rises, it becomes 1. At this point again this is 0 but this is 1, so again comes down. So there is a pulses, small width pulses or markers come depending on this jitter you have, and you will see once this kind of output voltage this, then you take an average of this. Is that correct? How do you take average? Filter. Okay, so you will get only average value of that. That value you feed it to V control and adjust your frequency. Is that okay? The point is trivial, but that's what it is. I just copied from Razavi, okay, some other things. This is of course is trivial. As I said, this is the DLL part. Essentially, it's only simple digital phase lock loop which is shown here. Okay. There is also a problem of jitter in PLL. There is a jitter in signal and jitter in phase lock loop. So अभी उसका भी एक issue है. Second loop दिया, उसका stability issue आ गया. Okay. So there are issues and issues. Okay. The 4 cases that I have discussed. If between the two V1, V2 there is no change in phase, so only at the, for a very short duration transitions occur, so the output also transits, okay, because this, even if we say it is 0, it is not never 0, so it is marginal whatever, so it gives markers. However, if it is pi by 2 as it is shown here, 50%, so for this time 0, but half the time there is 1, so you get an output of square waves of this kind. Is that correct? 50% of time, you can see here, this is 1, this is 1, so 0, but this is 0 and this part is 1. So wherever 1 0 occurs or 0 1 occurs, XOR will give you 1, okay. So correspondingly you will get such pulses, and what actually you have to do is the average of this, okay, is your control voltage. Integrator also can do the same. Okay. Then you have pi, opposite phase, opposite markers. The transition wherever goes strongly negative, we will show a mark on that. If it is 3 pi by 2, it will give a different frequency part in this, and you will get again pulses. So depending on the skews you have, you can always get the output, and this output when averaged can change the VCO frequency and bring it back to V2 and keep comparing between V1 and V2, so that finally they lock to a close by value. Up to 1 cycle, yes. 1 cycle phase range is this, phase detection is possible, and range is also, locking is also possible. More than 2 pi, it is second clock starts, no lock starts, it does not pick up. They should follow this model, rectangle model. So before we quit PLL, there are few interesting things about PLL which analog PLLs use, or analog signal processing people use, is they inject a sinusoid signal into reference input, which is the frequency at which you want the reference signal. The internal oscillator means VCO, lock the injected signal into reference, that is what you want, whatever this, it should lock to that. Phase or frequency difference between reference and injected signal is proportional to the K of the VCO, or if it is locked it goes to 0. And internal sinusoid then represent the filtered version of the reference sinusoid, and that is what you are looking, and that you use as your output of a VCO. Is that clear? एक simplest minus GMC filter के GMC oscillator के साथ minus GMC means what? Compensating the RP value. Okay, yesterday I showed you negative resistance this. Okay, here is the PLL base, PLL for a CMOS technology. This is your VCO minus GMOS VCO. Yesterday I had already discussed with you. These are the diodes which essentially receives the control voltage. This is that averager RC filter. I just showed you the LPF. This is that averager RC, and this is your phase detector, your reference input, the frequency at which you want to lock the input. And this is your VCO. You tune it to this, close to this frequency, feed it back, compare it, and the output here is locked to the reference. Or if you must have observed, there is no P channel device anywhere, still called CMOS, because technology is CMOS. ये VCO है, इसका control is coming from the phase detector averaged out. So this essentially why I say PLLs are very crucial for real life requirements, because you want to hold this frequency to a constant value before you use it into any particularly RF applications, okay, where this called image is very strong there and you will actually it will pass through the digital side and that may actually huge noise. Your capacitor requirement for A to D converter will be very large. So it is very difficult to maintain large capacitances in chip and therefore always you will try to reduce down frequency from the higher ones and you do not want images to move through. So no DC signal should go out, okay. So very important that it settles to a frequency exactly. Some other day, some other time. Before we quit this today, last introductory part which is again as I say not a part of the course but I think you should know before you quit. Switch capacitor circuits are very popular in A to D converters or many of the filters, okay. Like you can even make a ladder filter, LCR filter using switch capacitors. Why we want to change everything to capacitance? Because we know the resistance and inductance are always troublesome in taking areas and accuracies. Capacitors are well within my control. So I prefer all circuits to work with capacitors. So here is something very interesting. Let us take a case. This is your resistance. You have a voltage V1, you have a voltage V2. One of them is higher, let us say V1, so V1 minus V2 upon R is I, Ohm's law, or R is equal to V1 minus V2 by I, or V1 minus V2. What is current? Charge per unit time, okay, charge per unit time. But what is 1 upon time? Frequency. Charge is essentially Q times something and total charge will be decided by the capacitance available there some way into frequency, something of this kind, not exactly. So I have an idea that I can replace R's, ये CV करो ना इधर CV, okay. So I can replace a resistance by a capacitance. This is my thinking. This is what essentially it means. So here is one what we do. Okay. Let us say there are two switches which are driven by phi 1 and phi 2. Phi 1 and phi 2 are clocks which are what kind? Non-overlapping. Okay, so maybe I should draw. थोड़ा triangular बनाना चाहिए क्यों? क्योंकि actually rise time 0 नहीं होता है. If you want further you can do like this, okay. So essentially I am saying there is a dead time in which both signals are 0, okay. Both clocks are 0. Of course the period is same from this to this or from here to here, whichever way you look at the period is same. Okay, so here is a phi 1, phi 2 non-overlapping clocks and let us say I have a input voltage given here V1 and input output voltage expected there or actually put by me is V2. Do you see it is, I am trying to replace the resistance by this network, is that clear? V1 V2 V1 V2 बीच में जो R है I am replacing with two transistors, switches and a capacitor. Okay. If you have written down I will give the maths on that. Okay. So when the phi 1 is high and therefore phi 2 is 0, okay. So what is the charge on the capacitor? Q1 is CV1. If phi 1 is high, phi 2 is guaranteedly low. But they are non-overlapping है तो वो तो 0 है ही.
दोनों जीरो हो सकते हैं, but हाई है तो दूसरा जीरो ही है. So Q, that is the capacitor, is charged to potential V1 and holds a charge of Q1, which is C1 V1. Second time I close phi 1 and make phi 2 high. So during dead time it is retaining the charge of C1 V1. After some time my phi 2 starts. The problem why I kept dead time, because I don't want charge to be not reaching its maximum. I want that charge to be retained as the fixed value of DC, which I put V1. Okay. Now when the phi 2 goes high, the charge on the capacitors from this side, you can see this is V2 and this is your capacitance. So this is like a switch closed. Okay. This is like a switch open. Okay. So now this tries to charge this capacitor. Depending on initial, it will decide what the new charge should be, but assuming the charge which it should go, if initially there was no charge, should be CV2. However, if both are 1 by 1, so the net charge on the capacitor, assuming C1, V1 is higher, is Q1 minus, which essentially is C V1 minus V2. In one clock cycle of the phase, Q1 minus Q2 is the average current which is flowing through this, charge divided by time. So this is the average current, which is essentially equal to C V1 minus V2 divided by T. But we know from our earlier theory, current is essentially V1 minus V2 by RS or whatever our switch capacitor equivalent, maybe we'll say it. The equivalent resistor है वहाँ पर, तो V1 minus V2 by R, that is the I current flowing through this. So if I equate this, the switch capacitor is T by C, or equal to 1 upon F clock. So if I know my two-phase clock and I know its frequency, I can create a resistance of 1 upon Fc equivalently. Is that correct? Before we quit, we make a simple filter. एक छोटा सा, क्या यहीं पे कर सकते हैं? ये जो लास्ट फिगर है इसी को कर सकते हैं. So it will be C, RC time constant is C2 by C1 or C2 by C into clock, okay, 1 upon clock. R is 1 upon Fc, so if I want RC into C2, then it is C2 by C into 1 upon F clock. ये आपका पोल आ गया, कट ऑफ मिल गया आपको. You can see from here I can create any filter between these capacitors and an integrating capacitance. Also I can put switches there. Any resistor I want in amplifier, I replace that resistance by a capacitor switch, and then the ratio of capacitance will give you gains. So I can make an amplifier, I can make an integrator, because I don't put R there, I put only C, I get an integrations. So I can create every circuit of op-amp which requires R can be replaced by a switch capacitor. What is the advantage? Because capacitance are the easiest to make in MOS technologies or even bipolar technologies compared to every other resistor or any other values you want to fix. Okay. It's partly digital because switches are there, and that is where the problem started. Before we quit, no reason to explain, but these switches are not ideal. Okay. Now they create hell of an issue. One problem is, which everyone should know, whether it is digital, analog circuit, non-circuit. If when it is on, there is a charge in the channel. Okay. When you make phi 0, you expect this charge to collapse. So where it can collapse? Either at the source end or at the drain end. charge has to be withdrawn. But there is a capacitor sitting here, okay, उसको चार्ज कर देता है. So जो next value है वो एक ऑफसेट लेके शुरू हो जाती है. तो इसको किसी तरह से ये देखा जाए कि ये यहाँ जाने के पहले एक इधर कुछ और सर्किट डाला जाए जो वो चार्ज पिकअप कर ले. सोचो क्या बना सकते हैं जो कि एक और ट्रांजिस्टर डालते हैं जिसका सोर्स ड्रेन शॉर्ट कर देते हैं. ये वाला एंड यहाँ देते हैं फिर तो ये चार्ज इसमें चला जाता है और इसके आगे फिर कैपेसिटर है. एक और टेक्निक है एक चार्ज इंजेक्शन को हटाने के लिए. दूसरा प्रॉब्लम स्विचेस में ये है कि यहाँ पर कैपेसिटेंस हैं. They share the charge, feed forwards, feedbacks, both are possible. So output levels are decided by what frequency you are turning on and off and what is the feedback it receives. Okay. So the final voltages are not exactly known, depends on the frequency which you operate. This is another problem. Much probably this feed forward, backwards problems are very difficult to solve but can be minimized. इसका एक और मेथड है, इसको एक CMOS बना दो, पार्टली सॉल्व हो जाएगा. तीसरा प्रॉब्लम क्या आता है किसी भी डिवाइस के लिए आजकल KT/C noise and that KT/C noise always exists. So switches being non-ideal, the issues of non-idealities play a role in any switch capacitor systems. Okay. But otherwise they look to be very promising. Okay. They look to be very promising. Okay, so this finishes whatever I wanted to tell you in this course. Not that it is enough, not that it is less, but this is enough for this semester.